All right, so we're gonna do number 3. For number 3, we have a matrix 3 by 3, and we want to. Well, no problem. I'm glad to help. I'm here for that. I'm here to help. So we want to figure out whether this matrix is diagonalizable. So we still have to go through the steps of finding the eigenvalues and the eigenvectors. That's really what diagonalizability is based upon. First of all, diagonalizability. So hold on 1 second, guys. Hold on 1 second. Okay, so I want to find out the eigenvalues. So I want to find eigenvalues of A. So what are the eigenvalues of A, and how do we find the eigenvalues? There are 3, 5, and 3. Wow, so good, Baldwin. How did you get it though? How did you find the eigenvalues? How does one find eigenvalues of a matrix? Baldwin, so Baldwin, how did you find it? And since it's only 3 of us, I think it's okay if if you can maybe say it. Yeah, so you start using the formula A minus lambda I. That's right. So you have to find the determinant of A minus lambda I, set it equal to 0, and this will give you the characteristic polynomial. Remember? So this is the characteristic polynomial. So then we do 4 minus lambda, 3 minus lambda, 4 minus lambda, 2, 1, 0, 0, 2, 1. Determinant equals 0. Right? And so then what did you do? How did you evaluate the determinant of this matrix? You use row factor expansion, right? Or column factor expansion, one of those two. But which one would make more sense to do in this particular problem? So how do you find the determinant of this matrix? Or how did you find, Baldwin, the determinant of this matrix? Yeah. So, well, it's not going to be the row. Well, you could use a row, but there's one column here that makes more sense to use because it has two zeros. It's instead of only one. So remember, the determinant can be found utilizing row factor expansion or column factor expansion. So the second column, that's right. So we do column expansion along the second column. So then the zeros here, we only have to worry about the 3 minus lambda. So we got 3 minus lambda multiplied by, and then when we take the 3 minus lambda, we strike through the second row and the second column. And then the matrix that appears after I do that, I make the 2 by 2 matrix. And now I want to find the determinant of that 2 by 2 matrix. And when I do that, I get 3 minus lambda. I got 4 minus lambda squared minus 1. And then this is 16 minus 8 lambda plus lambda squared minus 1. And so we get lambda squared minus 8 lambda plus 15. 3 minus lambda equals 0. And then we can, and again, this is the characteristic polynomial. And then we can factor this even further, right? Negative 8 multiplies negative, adds to negative 8, but multiplies the positive 15. So it's going to be lambda minus 3, lambda minus 5. Right? And so then I can factor out a negative from this one here, and I get negative. This becomes lambda minus 3, and there's two of them, squared. Lambda minus 5 equals 0. And this is the characteristic polynomial in its factored form. And so the eigenvalues, when we solve for this, right, what are the eigenvalues? We get that lambda equals 3 and that lambda equals 5 when we solve it. So correct. Do we have to put in characteristic polynomial form on the exam? So if you look at the previous problems, right, it specifies find a characteristic polynomial. So you should be aware that you may have a problem where it specifically asks find a characteristic polynomial. And the way you express the characteristic polynomial could be in factored form. That's why I specify this is in factored form, because sometimes the polynomial could be in standard form of a polynomial, which you would get like lambda cubed plus lambda whatever, blah, 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 right? You can also express your polynomial in that regard, because that's the way we usually express polynomials. But in this, because of the way the determinant came about, the way we compute it is very nice, because it's nice and factorable. And so if your question if I had a question here, right, that utilize this matrix, I can say, hey, first find the characteristic polynomial. So I'll have part A, find characteristic polynomial of A. So that would be the first thing here. Boom, I found it. Part B, find the eigenvalues. Part C, find the eigenvectors. Part D, find the algebraic multiplicity. Find the geometric multiplicity. So all of those things could be possibilities as on the exam. So for example, eigenvalues of A, boom, I have them. Lambda equals 3, lambda equals 5. So I feel like a lot of this a lot of these kind of problems, right? It's like you're doing bookkeeping. It's like you're, like you're becoming. Okay, so yeah, I'm gonna talk about that. I was gonna say that it's like you're becoming the entity, the object that creates the receipt. Like, think about A, and you want to know all the specs, quote unquote, of A. And what you're doing is you're just learning how to look at a matrix and find out all its specs. And one of those specs are eigenvalues. So you're trying to, you're just getting, you're learning how to do that. And so part of this problem asks you for the algebraic and geometric multiplicities. So the algebraic multiplicity comes directly from the characteristic polynomial. So what are the algebraic multiplicities? Well, the algebraic multiplicities is how many times in the factor form of the polynomial does the lambda equal 3 factor, like how many times does it exist? So here we see a 2, and this 2 is associated with the factor lambda equals minus 3, which gives me lambda equal 3. So lambda equals 3 has an algebraic multiplicity of 2. This is for lambda equals 3, has a multiplicity of 2 because you see it twice. And then lambda equals 5 has a multiplicity of 1. So at the moment, that's all we can say. Okay. Now, when we talk about geometric multiplicities, we have to figure out what's the dimension of the eigenspaces in relation to the eigenvalues. So I want to find the eigenspace. The eigenspace for lambda equal 3. What does that make? What does that mean? That means I'm looking for the null space. I'm looking for the null space, right? This is the null space of A minus 3i. That's what the eigenspace means, okay, guys? The eigenspace is the null space of A minus 3i. Remember, all of this comes from this very straightforward. It comes from this equation. And when we looked at it, right, we solved that this looked like this. This equation here, guys, is a homogeneous equation. This is a matrix. This is a column vector equals 0. And what we're saying is that this V, whatever this V is non-zero. If it's non-zero, then that means that the null space of this matrix has to have something other than the trivial solution. It's a non-zero vector. And that's what we're looking for. And so that's why now we do A minus 3, right? So it's going to be A minus 3. So this is 3, this is 3, this is 3. So this will be 1, 0, 1. So you're going to have a 1, 0, 1, and then everything else will stay the same. So you get 0, 1, 2. And you get 2, 1, 0. And this is my matrix. Now from here, look what's going to happen. Look what you see. You see, you have to put this in row reduced echelon form. But you notice that these rows here are all scalar multiples. Well, these rows are the same. 1, 0, 1 and 1, 0, 1 are the same. So I can clear that bottom row and I get a row of zeros. And then look at the next row. 2, 0, 2 is just a scalar multiple of 1, 0, 1. So this also becomes a row of zeros. And the only thing that exists is the top row. And remember that top row or this matrix is in correspondence to the x1, x2, and x3 variables. So the only thing we're left from the row reduced echelon form is that x1 plus x3 has to equal 0 because we're solving a homogeneous system, right? So it's like saying we can also say that we have an extra column of zeros, but it doesn't really matter because it's just equal to 0. So we get that. What do we get? What do we learn? There's only one pivot variable. And there's what? There's two free variables, right? So x1 is equal to negative x3. x2 is equal to x2. And I can just call this s. And then x3 is equal to t. So this equals negative t. So what's the null space? What's the null space of a minus 3I? Sorry, this not little I, but big I. What's the null space? It's going to be what? The vector x is going to look like this. Negative t, s, and t. But then we can decompose this as t, negative 1, 0, 1, plus s, 0, 1, 0. Guess what I found, guys? Guess what I found? What are these vectors here? These vectors are the eigenvectors. Of what? Of lambda equal 3. Again, this is the null space, right? And this null space is represented by a linear combination of eigenvectors. These eigenvectors are linearly independent. So they're linearly independent and they span the null space. So what does that mean? That means that 1, 0, 1. So the set negative 1, 0, 1 and 0, 1, 0 is a basis for the eigenspace of null a minus 3I, right? That's what it's saying. It's an eigenspace. It's a basis of the eigenspace. So it's an eigenbasis. It's called an eigenbasis. So if that's the case, then what's the dimension? What's the dimension of the null space of a minus 3I? Well, remember what the dimension is? The dimension is the number of the basis vectors. So the basis vectors, the number of basis vectors here is 2. So the dimension is 2. And remember, the dimension of the null space or the dimension of the eigenspace, so let me write that down. The dimension of the eigenspace of lambda is equal to the geometric multiplicity of lambda. That's the important thing, guys. So the dimension of the eigenspace of lambda, which we found, is 2, which means that the geometric multiplicity of lambda being 3 is also 2. So then I can now add additional information about these eigenvalues and its geometric and algebraic multiplicities. So we got geometric multiplicities. And this equals 2. And this will also equal 1. So then let's show that. Now let's look at the eigenspace for lambda equals 5, which is the null space of a minus 5I. So we're plugging in 5 here. So 5, 5, 5. So this will be a negative 1, a negative 2, and a negative 1. So we're going to get the matrix -1, -2, -1. And then what else do we have? We had 0, 1, 2, right? So this is 0, 1, 2. And then what was that? 1, 2, 0? 2, 1, 0. Sorry. So this is 2, 1, 0. So this is my matrix, and I want to find its row reduced echelon form. The first row, the third row, they're scalar multiples of one another. So I have a 0 row in the bottom. And I got 1, 0, 1. And now I want to get rid of that 2 in the bottom, right? I want to get rid of the 2 underneath the -1. So I can multiply by this. I can multiply by R1, multiply this by 2, and add it to R2 into R2. So if I multiply this by 2 and I add this, I get 0. If I multiply this by 2 and I add it, I still get -2. And if I multiply this by 2 and I add this, I get a 4. But then I can make that into a pivot if I divide this by a 1. If I divide this by -2 and divide this by -2, so I get 1, -2, and I get 1, 0, 1, 0, 0, 0, 1, right? So that's the row reduced echelon form. So I should write this over here. Now, and this should be 0, pardon me. So then what information do I get from here? I get 2 pivot variables. So I got 2 pivot variables and only 1 free variable, which is what I should expect. Because the free variable gives me the dimension. The number of free variables tells me what's the dimension of this space. So this is going to be x1 equals -x3, x2 equals 2x3, and x3 is something t. It's some other variable, right? It's some parameter. So I call it t. So then what's going to be the null space of A minus 5i? So what is that null space? It's going to be the vectors that are of the form -t, 2t, and t, which can be written as t multiplied by -1, 2, 1. So what does this tell me? This is an eigenvector of lambda equaling 5. And it's the eigenvector is only one of them. So the the geometric multiplicity of lambda equaling 5 is the same as the dimension of the null space of A minus 5i. And the dimension is equal to the number of basis vectors in the basis of that space, which is only 1. Make sense?
Yeah, Professor, I just have a question.
Sure.
So why is there one vector for the null space of A minus 5a and 2 vectors for A minus 3a?
Are you saying why?
Yeah,
Well,
I don't understand the A minus 3a a little bit. That's all.
the A minus 3i.
Yeah, 3i, sorry, not 3a.
Yeah. So you're saying you don't know why you get 2 vectors here, but you only get 1 vector here?
Yeah.
Well, it's because of the very nature of this matrix. The nature of this matrix, A minus 3i, is this matrix, correct?
Yes, sorry.
So that's this matrix. It just happens to be this. And again, so a lot of these, like I mentioned, this topic particularly brings everything that you've learned basically and drags it all together. Like everything is at once here. So we're talking about the null space of a 3 by 3 matrix. Now, the null space This word null space, what is it? I think that may be the first thing you have to identify. What does it mean to be in the null space of a vector, of a, not a vector? What does it mean to be, or what does the null space of a matrix mean? Do you know?
Uh, Not 100%, but I don't know the correct definition, but
What is it? You see, these terms, right, are just being bounced around. Bang, bang, bang. So then you're like null space, no, the null space. What is the null space? If you don't know what I'm saying when I say the null space, then that's the first thing you should address. You should be like, wait, what in the world are you talking about? What is a null space?
I just thought it was like mapped to a zero vector. That's why I thought.
Okay, okay, we're onto something, but it's kind of a bit incomplete. So what is being mapped to the zero?
the the domain,
Okay, what is the domain?
the linear subspace, right?
Linear subspace. Okay, so I think a linear subspace. I'm not sure about what you mean by linear subspace. I think you're saying uh,
The whole thing. That's what I'm thinking.
what do you mean by the whole thing?
Okay.
Hmm?
Wait.
This is good. This is good. This is good. Let's go back. So let's just make it simpler, right? What's the null space of A? Just a matrix. What is it? The null space is the set of vectors such that AX is zero. That's the null space.
Yeah.
So if I write this in words, it's the set of vectors X that when multiplied by A equals zero. So in a sense, you can think of this as it's a solution space. It's when you have uh, a matrix multiplied by an unknown, and that gives you zero. We're trying to figure out what are all these unknowns. All these unknown vectors that do this procedure are going to be considered a set. And that set of vectors happens to be a space, a solution, a subspace of the domain,
Oh, okay. That makes sense now.
right? And so then A, right? If you want to get more technical, A is a representation of the linear transformation. And that's what we made that connection with linear transformations, which is a function. It's a very specific, special kind of function. It's linear. So linear transformations can be represented by matrices.
Yeah. I guess my problem was always the null space. Everything else I got just the null space I was very confused about.
Yeah. So the null space is a set of things, and those things are vectors. And those vectors are vectors which, when multiplied by the matrix that you're dealing with, gives you zero.
Zero, yeah.
So normally, or all the time, the zero vector is part of the null space.
Mm.
So x equaling zero is obviously, this is called the trivial solution. This is called the trivial solution. Why would we call it trivial? Because it's obviously going to be a solution to this equation. It's like saying, what's 5x equal to zero? What is x going to equal? Zero, obviously, right?
Yeah,
So
yeah.
when we have a matrix, it doesn't matter how big, how small. If you multiply it by a column of zeros, And if you multiply that matrix, it can have a million entries. You multiply it by a column vector that multiplies every row with zeros. Obviously, you're going to get zero at the end.
Yeah,
That's
yeah.
why it's called trivial. However, not the null space is not always just containing the trivial solution. This occurs. This occurs when the matrix itself is not invertible, and so that's why when we talk about invertibility of matrices, one of those equivalent statements about invertibility is the fact that if you have an invertible matrix, only the trivial solution exists in the non-homogeneous system. This is called a this is called a homogeneous system. Why is it called homogeneous? Because every, remember, the matrix here represents a system of equations. So you can create a system of equations where everything equals zero. When you have a system of equations where every equation equals zero, it's called a homogeneous system. It's homogeneous. So when we have a homogeneous system, right, such as this, and the matrix that you get is not invertible, then that means that the trivial solution is not the only solution that exists. If
Mhm.
the matrix is invertible, then only the trivial solution exists. Why is that? Because if it's invertible, ax equals 0, I can solve it by multiplying by the inverse. And the inverse here there's only a unique inverse. That's the whole point. It's unique. Because it's a unique inverse, there's only one inverse that works. And x has to equal 0 and only equals 0. That's only if the inverse exists. If it doesn't, which is exactly what happens here, you see this? I already know this, the inverse doesn't exist to this. Because, and so then this goes back to that list of equivalent statements, which all of you should know like the back of your hand. Because a matrix is not invertible, it also means that the row reduced echelon form is not the identity. If this matrix had a row reduced echelon form of the identity, that would imply that the matrix is invertible, and that would imply that the solution, the null space of that matrix, would be simply the trivial solution. But the whole point of this, the whole point of this is that V from the very beginning was non-zero, meaning that V is in the solution space of A minus lambda I. In other words, V is in the null space of A minus lambda I, and that V is non-zero. If you have a solution space where it contains an element that's non-zero, this implies that this matrix is what? Not invertible. So we automatically already know that the null space of these eigenspaces will be something other than 0. And how do we solve a system that has a non-invertible matrix? We perform row operations to find the row reduced echelon form of the matrix. And that's what we learned in the very beginning. We learned how to solve systems of equations by performing this Gauss-Jordan elimination on the matrix. And now, based upon that, we can solve. And it just so happens that in finding the row reduced echelon form of this matrix leads us to expressing a vector that has two free variables. Because we have two free variables, that implies that we have two vectors that are independent of one another, and each of those vectors are eigenvectors. So the reason why the null space of A minus 3i has two vectors such as this is because of the nature of the row reduced echelon form of the matrix. It's telling us we have two free variables. Because we have two free variables, we have two degrees of freedom. The 2 degrees of freedom implies that we have a dimension of 2.
Yeah, thank you, Professor. I appreciate it.
Does that make sense?
Yeah, yeah, it definitely did.
And the thing is, this doesn't always happen. That's the whole point. That's the whole point. It goes back to what it doesn't mean to be diagonalizable. What does it mean to be diagonalizable? It means that you have sufficient eigenvectors What does that mean? If I have a 3 by 3 matrix, then that means that I must have in order for this to be diagonalizable, I must get 3 eigenvectors. I got 1, I got 2, and I got 3. I got 3 eigenvectors. So because I have a 3 by 3 space, a 3 by 3 matrix, I'm dealing with the space R3. So I'm going to get 3 eigenvectors from this, which is great. There can be such situations, however, where you have, for example, a repeated root, right? Lambda equal to 3, where the algebraic multiplicity is a 2. But you can have, and we've had instances where the null space of that eigenvalue that repeats more than once can produce vectors that could actually not produce enough vectors. So we've had situations where the algebraic multiplicity does not equal the geometric multiplicity. In those cases, the matrix is nothing's wrong with the matrix. It's just that it's not diagonalizable. That's all. So in this case, it is. Why is it diagonalizable? Because the algebraic multiplicities and the geometric multiplicities match up. What is so significant about having these two match up is that this is saying this is algebraic multiplicity 2. Geometric multiplicity is 2. What does that mean? The geometric multiplicity being 2 means that we have 2 eigenvectors in this space. And we have 1 eigenvector in this space. So that completes the 3 that we need because we're in the space of R3. We're dealing with a matrix that takes things from R3 and puts it back into R3. Okay, so now we're pretty much done. So I just want to write it out again. So the eigenvalues is 3 and 5. The eigenvectors I'm going to use what is it? Negative 1, 0, 1 and 0, 1, 0. Negative 1, 0, 1 and 0, 1, 0. And the other one is negative 1, 2, 1. And of course, these two here are from the lambda equaling 3 eigenspace. And this one here is from lambda equaling 5. So then we can create a matrix now called P. And P is going to have the eigenvectors along the columns. So this is 1, 0, 1. This is 0, 1, 0. And this is negative 1, 2, 1. So if I were to multiply this, let me see how this looks like. It's saying if it's diagonalizable, right? So let me just, I never mentioned it. So A is diagonalizable because there are sufficient eigenvectors. Which is a total of 3 that we needed. Because our matrix A represents a transformation from R3 to R3. And another way you could have said this is that the algebraic multiplicities of each eigenvalue equals its geometric multiplicities. Okay. And so then let me just see what this is saying. It's saying if you find it, I gotta correct this. This is negative. It should be a negative. I'll make that correction. This should be negative. So what this is saying is that if you do have a diagonalizable matrix P, A, then you can make A into a diagonal matrix by multiplying the left side by the inverse of P, multiplied by the right side by P, and the diagonal matrix would be what? The diagonal matrix would be the eigenvalues. 3, 3, 5. The 3 will repeat twice because it repeats twice. And so then we would have what? What is A? A is that matrix, right? That we started with from the very beginning. So it's 4, 2, 1, 0, 3. Let me just. So this is my A. And then my P is going to be negative 1, 0, 1, 0, 1, 0, negative 1, 2, 1. And then P inverse is going to be P inverse, whatever that is. You can check it on a calculator. That when you multiply these things together here, you indeed get a diagonal matrix as such. Okay? So voila, here we have. So that's what this problem entailed. So it deals with a lot, right? It deals with finding eigenvalues. Eigenvalues deals with the determinant of a matrix, which you have to know what the determinant is. Solving the polynomial, you should know how to solve it. Then once you have the eigenvalues, you find the eigenspace, which is the null space of A minus lambda I. You find the null space by finding the row reduced echelon form of that matrix. The row reduced echelon form of that matrix A minus lambda I gives you the information about the vectors in the null space, and those basis elements of those eigenspaces are called the eigenbases, which are the eigenvectors. Well, no problem, man. Have a good time. Hope you get better. All right. Okay, so no problem. No problem, man. So Baldwin, does this make sense? Great. So then a lot of these problems are basically the same thing, right? In the review sheet, diagonalizability, it's just the same thing. And of course, related to that is this whole section on eigenvalues and eigenvectors. Diagonalizability just takes it one step further and asks you whether or not it's diagonalizable. So anything else? Okay, good. Do you have any other questions about anything here? Yes. Those free variables, you can think of them as the degrees of freedom, which is exactly what the dimension, you can interpret dimension as being so. The dimension of a space, vector space, you're dealing with what are the degrees of freedom. And so those free variables are the degrees of freedom.
Okay.
Because you can say, hey, T can be anything, S could be anything. So you have two choices that can be anything. So that gives us a two-dimensional. This is a two-dimensional. This is a plane. Do you see that? This is a vector in a three-dimensional world. And we're saying is a linear combination of these two vectors. If you take two vectors in three-dimensional space and you take a linear combination of those two vectors, you create a plane. Or in other words, if you take the span of these two vectors in three-dimensional space, the span is all linear combinations, which is exactly what this is saying. All linear combinations of these two vectors. If you were to take all linear combinations, you create a plane. And a plane has a dimension of 2. And then this thing here, this null space here is just one-dimensional. One-dimensional, a span of one vector that's in three-dimensional space is simply a line. So you have a plane and you have a line. And if you take a linear combination of those spaces, right, of something in here and something in here, and you take a combination of those, then you have the whole space R3. So eigenvectors, we have a complete we have a complete basis that are made up of eigenvectors for the entire space R3. So isn't this cool, right? I think it's cool because the reason why I think this whole idea of linear algebra here that we've learned so far is interesting and cool because in the beginning of the semester, you all were just trying to make sense of what a matrix was, which is just numbers organized with rows and columns, and that was it. That's it. How do you add them? How do you multiply them? Great. Oh, we do this additional stuff with row reduced echelon form, and you're getting used to the mechanics of dealing with numbers in a grid-like fashion. So you're dealing with the mechanics. Now that you took care of the mechanics of it, now it's like, okay, let's talk about the matrix and what does it represent? And what are the null space, the eigenvectors, now this is more information about the matrix, and it's beyond just the mechanical and computational aspect of it. Now you're dealing with space, vector spaces, subspaces, and now you're talking about span, and you're talking about linear independence, and then all of this is much more theoretical, much more profound than just, find a row reduced echelon form of a matrix and just stopping there.
Yeah.
And that's what's interesting about this whole thing, because now the matrix itself is not just numbers, it's space. You're dealing with space in a mathematical sense. Okay, so wait, let me get this one. So we want to find the LU decomposition. Okay, so let me take a screenshot of this. So find the LU decomposition of a 2x2 matrix. So remember, there was a procedure, and I think we talked about it in, no, this is not what I think 23. The LU, remember? This is a procedure right here. So we reduce the matrix A into its row echelon form, REF. And then we find L to be the reciprocal, right? So it's basically everything that we do is just the reciprocal of the multipliers, and it's the negative of the multipliers used to make the zeros below. So for those numbers that we use to produce the ones in the pivots, it's going to be the reciprocal. And then the numbers that we use to make the zeros underneath the number, the pivots, we're going to take the negative of that. So just briefly, look what we did for this matrix A. I want to find the LU, right? The LU decomposition of A. So I first want to find A and find the row echelon form of A. And that's going to be my U. So automatically I get the U immediately. So how to get the u? Well, I make this into an upper triangular
Okay. And
matrix.
then the L would be the lower triangular, right?
It'll be lower triangular, right? But then the upper triangular, the way we do it is that the diagonals have to be ones. So
Okay.
diagonals here are ones, right? And so whatever we get, that's our u. But how do we get our L? Our L, remember, are going to be the diagonals are going to be the multipliers, right? That make my that we use to make our pivot variables equal to 1. So for example, in this step here, I made this entry, which was originally 6, into a 1 by multiplying the first row by 6. So that's the first entry here, 6. It's going to be the reciprocal of 1, 6. It's 6. And then if you look at this next step here, I got this 2 here. So how to get rid of the 2? Multiply it by a half. So the diagonal, the second diagonal, deals with the second pivot. And I multiply by a half, so I multiply by the reciprocal, 2. What happens is to get the third guy here, I didn't have to do anything. I didn't have to multiply directly by a number. It just became a 1. So that's why this 1 here is untouched. Now, how do we get these numbers here? These numbers here deal with the what we multiplied to get rid of these zeros here, to get rid of these entries here. So to get rid of this 9, I had to multiply by -9. To get rid of this 3, I had to multiply by -3. So these are going to be the opposites of -9, which is +9. The opposite of -3, which is +3. And then to get rid of this 8 here, I need to multiply by -8, right? And put it +8 here. So that's the way. So to do this, we first do what? Row echelon form, right? So what's the row echelon form of this guy? And one thing about LU decomposition is that we're not going to switch any rows. So that's the only thing that you have to keep in mind. Do not switch rows. Because if you switch rows, then you kind of mess things up. You mess up the LU decomposition. So you're not going to switch any rows. We can only multiply a row by a single scalar, or we add a row of a scalar multiple of another row. So the first thing we do here is what? 1/2 R1 into R1. So this becomes what? 1, 4, -1, -1, right? So automatically my L already, I know that I'm going to have a 2 here. Do you see that? I already know that. Why? Because of this 1/2 here. Okay? Then I want to get rid of this -1 here. How do I get rid of this -1? Just add R1 plus R2 into R2. I should write this different color here. So we do R1 plus R2 into R2.
So then this would give us a 1, right?
This would give us a -1.
Okay.
Because we're doing the opposite, -1. And then this becomes 1, 0. This is 4, right? And then this becomes 3, correct? But I want the diagonals of my u to all be 1. So I have to do one more step. I do 1/3 R2 into R2. This is 1, this is 4, this is 0, this is 1. So then what does that mean? That means I must have had a what? A 3 here. And this is my u. And so this is it. So my A, which was what? 2, 8, -1, -1 equals L 2, -1, 3, 0 multiplied by U 1, 0, 4, 1. And what's supposed to happen is that when you do this multiplication, right? I get 2. And then you get, how do you get 8? Do this times this. I get 8. How do you get -1? You get this row with this row, you get -1 column. How do you get this -1? You do this times this, which gives you -1. So this works out.
Okay.
And then the same thing goes for 3 by 3, 4 by 4.
We just got to keep in mind we can't switch the rows, right?
You can't switch the rows. Because if you switch the rows, then there is no structure of this. There's no way that you can specify that. Yes, it just derails the whole
Mhm.
notion of decomposition. It just, yeah.
I see. Well, thank you, Professor.
Okay, no problem, Alderman.
Unfortunately, I had to like get going.
Yeah, no, it's okay. I understand. Don't worry.
So, yeah, Professor, I don't know.